imagine you are sitting in a car hurtling at a speed of 40 kilometers per hour when boom, you collide with an oncoming car also going at 40 kilometers per hour. But you see ahead of you in an instant the metal on your car crumbling up and deforming, which you may think may be quite expensive to fix, but in reality, this metal is crumpling up to absorb the force from the crash being transmitted upon you, keeping you idle and potentially saving your life. It can be crushed in a head-on collision with another car, a collision with a solid wall such as a concrete barrier, or a rare collision. The energy is generated by the kinetic movement of the accelerating car, and so the sudden interruption in this accelerating body can cause the energy to be expelled upon or wherever the car is being crashed upon. According to a British Motor Insurance Repair Research Centre study of where the vehicle impact damage can occur, 65% were front impacts and 25% were rear, which is why crumple zones are located on the front and the back of a vehicle, where also the engine and the boot space can be located, and so these parts are also made of materials that can easily crumple. The beauty of crumple zones is that it keeps you in your present position due to the inertia associated with a crash, which would send you flying forward as your body is used to going 40 kilometers per hour, the speed of the car. However, after the crash, the car has been forcibly stopped by a collision, and the crumple zone can bring the car to a sudden halt and take in the force which would have otherwise been transmitted upon the occupants. And the force is taken in by the crumpling pieces of metal in conjunction with the airbags and seat belts in their present position and not flung forward where they could be exposed to debris or shattered metal or glass, or even be flung outside against the road, against all of which could lead to serious injury or death. Newton's third law of motion states that an object in motion stays in motion with the same speed and in the same direction, e.g. 40 kilometers per hour, unless acted upon by an unbalanced force, which can be a sudden halt from a crash, or a solid or a concrete wall. And so when a car is travelling at a constant speed, all the passengers are carried along at the same speed. When brakes are applied and the car comes to a gradual stop, your body is used to travelling at that constant speed, and so you are thrown forward. The same thing happens when the car moves. Your body is hurtled back as it is so used to staying idle and stationary. These cars are travelling at 40 kilometers per hour, a safe speed and maximum speed for a school zone, and a head-on collision would equate to a force of 80 kilometers per hour affecting both vehicles, and would be the same force as a normal car colliding against a solid surface at 80 kilometers per hour. Now, in terms of force, to calculate the force of these cars, we need to look at the following equation. The formula is F is proportional to M, where M equals mass and F equals force and A equals acceleration. For example, a Mazda car would have a mass of around 1,700 kilograms, and an example of an acceleration speed could be 40 kilometers per hour, which would be 11 meters per second. Now, if we times 1,700 by 11, we get a force of 18,700 newton. Car having a greater motion, the more, and having a greater mass, which would lead to increased inertia and a greater resistance involved, as there is a huge change in motion, and the crumple zones will need to be able to take